Okay, so picking up part 3 of the 1-5 notes here, we left off talking about the difference between the instantaneous and the average acceleration. So just to close on that thought, how do we find the acceleration, the average or instantaneous, if I'm given a velocity versus time graph? Right, we've talked about this a little bit before, but just to recap it. So if I give you a velocity function that does whatever it may do, something like this, if I asked you to find the average acceleration between maybe, say, this point here and this point here, right, the average acceleration would just be the change in velocity over time. So the average acceleration would look something more or less like that. It would just be the slope of the secant line between those 2 points. Whereas the instantaneous, right, would be the acceleration that is tangent to the curve at either one of those 2 points or at any location along the way, right? So if I asked you what's the instantaneous acceleration down here at 5 seconds or whatever this may be, right, that would be my acceleration, would be the tangent line slope. Okay, so obviously again, you've seen the algebraic side of doing that using the velocity or the acceleration functions. You need to know the graphical side of that too, though, so make sure you are comfortable with that. And then how do we find the velocity given an acceleration versus time graph? So how do we go the other direction? Well, again, we've referenced this a little bit already, but if I give you an acceleration versus time graph that does whatever it may do, then to find the change in velocity, you'd find the area underneath the curve. So again, that would represent a change in velocity. The area underneath the curve would represent a change in velocity. Keep in mind, any area bounded up here above the x-axis would be a positive change in velocity, and any area down here would be a negative. Right? We know algebraically, calculus-wise actually, right, we would do the integral, find it, but make sure you're comfortable with graphical representations too. But anyway, let's do a few more examples and then we'll be done with this section of the notes. So examples 5 and 6 here. Example 5, a particle's velocity is given by this function. Each of these are standard units. What time or times are the turning points in this particle's motion? And then B, what are the particle's displacement from where it started and acceleration at the turning points? So for part A, this goes back to what we looked at early in this last section here. If I want to find the turning points, I need to find out when the velocity goes from either positive to negative or negative to positive. So I'm looking for where is the velocity equal to 0, and then I need to make sure that it is in fact turning around at that location. Okay, so if I just set this, if I substitute 0 in for velocity, and then I have this equation to work with. Now you obviously could FOIL this out, right? You could distribute this out and then solve it from there. But I could also, if I set it equal to 0, just solve it from this point. Right? I'm actually just going to add this whole quantity to both sides. So I get t minus 5, that whole thing squared, equals 10. So then I would square root both sides. The only thing you do have to be very careful about when you square root both sides, right? Obviously I get a plus or a minus radical 10. So I am going to have two separate possible answers here. And then my last step would be to add 5 to both sides. So I have two possible times where I may turn around. One time would be 5 plus radical 10, and the other possible time for a turning point would be 5 minus radical 10. Okay. If I was doing this algebraically, so maybe you're taking the AP test and it's multiple choice and you don't have a calculator available. Okay, so if I was doing this algebraically, the way that I would have to do that is I would take my function up here and I would plug in a value that is a little bit less than this time and a little bit more than this time, and then see if they go from positive to negative or negative to positive. So what I mean by that is this. I know that the square root 10 is about 3 point something, right? I'm not even worried exactly what it is, but I know it's more than 3 and it's less than 4. So then 5 plus that would be 8 point something. So the numbers that I would check if I was doing this algebraically, I would plug in 8 to my original function. So I would do t minus, or excuse me, 10 minus 8 minus 5 squared, since 8 is a little bit less than this number. So obviously 8 minus 5 would be 3, that squared would be 9, so 10 minus 9 would give me 1, which most importantly is a positive 1. So I know that the velocity just before this time was positive. So again, before that time of t1, it was positive. Then I would choose a number a little bit bigger than the 8 and whatever change we had. So I would choose 9. So I would do 10 minus 9 minus 5 squared. And then 9 minus 5 obviously is 4. 4 squared is 16. 10 minus 16 is negative 6. And again, the most important piece right here, it's a negative. So I now do in fact know that I went from a positive value to a negative value, which tells me that this is definitely a turning point. Again, that tells me that that is for sure a turning point. You could do the same thing for this. So again, this would be 5 minus 3 point something. So then this would be a 1.89, somewhere in that ballpark. And then if I wanted to choose a number smaller than that, I could choose 1. If I wanted to choose a number bigger than that, I could choose 2. Okay, so I could do the exact same thing. If I do, I find out that this one actually then goes from negative to positive as well. So both of these are in fact turning points. Now, if you had your calculator, I wouldn't recommend wasting time by plugging in. Instead, you could just plug in the actual function, right, and just get a picture of your graph. And if you did that, you'd get a graph that looks something more or less like this. And again, I'm not worried about specifics, but it would give me a graph that crosses here at 5 plus radical 10 and at 5 minus radical 10. And actually, it'd probably be the other way around. Probably look more like this, but it doesn't matter. The point is, it would go from a positive to a negative and vice versa. Okay, so both of those are in fact turning points. If I had a graph, I could quickly check that, but I would still be comfortable algebraically solving this as well. So then for part B asks us what's the particle's displacement from where it started in, what's its acceleration at those turning points. Well, to find its displacement and its acceleration, the easiest thing to do is just to use our calculus, right? So we know that our original function was t minus, or I keep saying t, 10 minus t minus 5 squared, right? So I've got my original function there that I'm working with. I want to find, because this is my velocity function, I want to find the derivative of this to find my acceleration, and I want to find the integral of this to find my position. Well, obviously right now it could be pretty tricky. You guys maybe aren't comfortable yet with the chain rule and all that fun stuff. So then the other option would be, let's just go ahead and distribute this. Let's go ahead and FOIL this out, which I am going to do here real quickly. So I get a function that looks something like that, and then distributing the negative, of course, right? So I actually get this to be my velocity function, which you could have used from the get-go, but obviously you could have used that as well. This makes it easier, though, to find the derivative. So if I want to find the derivative, I find my acceleration function. So I would bring the 2 out front, it would be negative 2t, and then I'd bring the 1 out front, so plus 10, and then the negative 15 would go away. So then to find my acceleration at those two given times, again my times were 5 plus radical 10 and 5 minus radical 10, all I have to do now is substitute this into the function. So the acceleration of 5 plus radical 10 equals negative 2 times 5 plus radical 10 plus 10. Right, I just plug that in. Same thing with my other one. 5 minus radical 10 equals negative 2 times 5 minus radical 10 plus 10. Okay, so obviously I will leave it up to you guys to calculate that just to make sure, but you do get two different accelerations, although they're similar accelerations. They're related in a way, but you do get two different answers then for the accelerations at those two times. So hopefully you're okay with that. But I do want to make sure we have plenty of time to discuss the position. So I'm going to go ahead and leave the calculation for that to you. So to find the position, right, I need to do the integral, because the derivative of the position is the velocity. So in order to find the position function, I need to do the integral of my velocity function. Well, integration, like we've seen before, right, we will make this power 1 bigger and then divide by that new power. 1 bigger, divide by the new, 1 bigger, divide by the new. So my position function would be negative 1/3 t to the third plus 10 divided by 2, because that new power of 2, so 5 t to the second minus 15t, and then do not forget, it's easy to do so, but don't forget that plus c. It is very important we don't forget the plus c. Now in this case, if I go back to the question, it didn't give me any data to work with, but it did say, what are the particles' displacement from where it started? And the significance of that statement right there is that allows me to define the initial position as 0. So at t equals 0 seconds, I can say the initial position from where we started is in fact 0 because I'm just looking for the change in displacement. I'm looking for how far did it go from where we started. So then down here, even though I didn't give you the point, you do have to interpret it. I now know that this is definitely going to be a 0 because when I plug in 0 for t, everything else goes away, which means c has to be 0 as well. Okay, so that's very, very important for us. But then once you've got that conclusion out of the way, you just find your position function the same way that we did with the acceleration. So you substitute 5 plus radical 10 into this beautiful equation. And again, I'm going to leave that to you guys to try that, and then you do the same here. Okay, so the other option would be you could graph this function and then trace this value to figure out what it is when you trace it. Okay, so the other option, if you don't want to substitute into that whole mess, you could actually just graph this function and trace these values. But I'm going to give you guys a chance to plot those points. If you are doubting anything on this or if you have trouble with it, obviously come find me and come let me know. So then the last example, hopefully a pretty easy one here. Example 6, they ask us, the figure below shows the acceleration graph for a particle with an initial velocity of 10, it is very important that they tell me that because I have no way of knowing the initial velocity by just looking at the graph. I can always find the change in velocity as the area under the curve, but I don't know where it starts unless they tell me that. So they ask me what is the particle's velocity at 8 seconds. Well, again, we're just finding the area under the curve. So you could either represent these as two linear functions and integrate, or I can simply find the area of this rectangle plus the area of this triangle and add those two together. So the area of the rectangle would obviously be a 4 by 4. It's not a rectangle, it's a square. So the area of that would be 4 times 4, so 16, plus the area of my triangle, which is 1/2, 4 times 4. So 16 plus half of 16, right? So 8, so 24. So my area is 24. It is worth noting that it is all positive area because it is all bounded above the x-axis. So that's all positive area, which means this was a positive change in velocity. So if I started at 10 meters per second, my final velocity after 8 seconds would be 10 meters per second plus the 24 that I have gained. So it would be 34 meters per second. The only other thing I want to mention, so hopefully again this one wasn't too bad, the only other thing I do want to mention, make sure you're comfortable with the fact that if it were below the x-axis here, we're bounding this area. We don't try to do anything goofy over here. I know that's the most common mistake that I see is people try to drop down. We don't do anything like that. We bound in the area between the curve and the x-axis, but this would be a negative change in velocity. So watch out for the little details like that. But like I said, hopefully example 6 was a pretty good way to end this section. This is the last section in Unit 1, so we will then have a review and a test coming up over this stuff.